We present an algorithm capable of using a single depth image to plan local collision-free trajectories for multicopters. The algorithm partitions the free space of the environment with a set of pyramids, and then uses the pyramids to efficiently check whether a given trajectory remains in the free space. Our trajectory planner can be used to generate local collision-free trajectories at a fraction of the computational cost of other existing planners. Thus, because of its computational efficiency, the algorithm can be run at high rates even on low-power computers not typically thought of as powerful enough to be used in autonomous flight. To demonstrate this, we implemented the algorithm on a vehicle equipped with an Odroid XU4, a low-power embedded computer. An Intel D435i depth camera was used to capture depth images, and an Intel T265 tracking camera was used to perform pose estimation. The vehicle was flown fully autonomously in a cluttered tunnel environment. We capture depth images at 30 Hz and run our planning algorithm for 30 milliseconds on a single thread when each new depth image is captured. In this case, the planner is provided only with a desired exploration direction and chooses the collision-free trajectory that will produce the fastest motion in that direction. When the vehicle comes to rest and is unable to find any collision-free trajectories, the exploration direction is simply rotated by 90 degrees. In the second hallway, the vehicle avoids obstacles hanging from the ceiling as well as several obstacles leaning against the walls. Each hallway is roughly 20 meters long and 2.5 meters in width and height. Here we see the onboard video captured during the same flight. For each 30 millisecond planning stage where a collision-free trajectory was found, about 2,000 candidate trajectories and 3 pyramids were generated on average. The planner was able to find at least one collision-free trajectory in 35% of the depth images captured. The vehicle traveled roughly 40 meters in 43 seconds, attaining a maximum speed of 2.6 meters per second. Note that although a simple heuristic is used here to determine the exploration direction, in practice a high-level global planner can be used to guide the vehicle, while our planner provides a guarantee that the vehicle will not collide with obstacles.